Hello, today I will be discussing Lab 1 titled Constant Velocity. The purpose of this experiment is to observe and model constant velocity motion in the scope of Newton's second and first law. Newton's second law can be modeled using the following equation, where we have the net force over mass is equal to change in velocity over change in time. Here the net force and velocity are vectors, and then mass and delta t are non-zero scalars. Given that we're modeling constant velocity, the final initial velocity should be equal, giving us a change in velocity equal to 0, therefore a net force equal to 0. This carries over directly into Newton's first law, which states an object in motion will stay in motion, and an object at rest will stay at rest, unless acted upon by a non-zero net force. So in the scope of our experiment, which assumes a net zero force, we can use these fundamental principles to model constant velocity and discuss discrepancies between what's observed and what we model. Moving on to my observations, I used the app Tracker to obtain experimental data of a soccer ball in motion. You can see here that I took out a total of 20 frames, and then I filmed out a constant frame rate of 30 frames per second. Here we have my real distance scale, and then we have my coordinate axes modeled so that the ball is going in a negative x direction. After extracting the data and putting it in Excel, I graphed it and I set a trend line. Here it's notable to see that the slope is equal to the change in position over the change in time, giving us velocity, and our r squared value is very close to 1, which means that there's a consistent linear relationship between position and time. Or in other words, it appears that the slope and the velocity is near constant, which is exactly what we want. I used GoScript to create a model, keeping in mind these two equations. This first equation is Newton's second law, solved for the final velocity. And then the next equation is the update position formula. Okay, so in the actual code, I have the mass set to the standard mass of a soccer ball in kilograms. I got the position vector from the data in Tracker. Similarly, I calculated the velocity vector using the data in Tracker with using the first two coordinates to get the velocity. I use those 2 points because I want the velocity to be very close to the instantaneous velocity. So using 2 data points that are very close to each other help in that. The while loop is meant to model a reiteration of Newton's second law. So I choose a delta t that's comparatively small to the total time. Here I set the net force equal to the 0 vector because we're modeling constant velocity. We have the velocity and position being updated based on the equations I had before. Note that the net force is equal to 0, so the final velocity and initial velocity are equal to each other. When I run the program, we see an object moving in the negative x direction, just like we observed. We have a linear relationship between position and time, and a constant velocity. Looking at a comparison between the two data sets, we see that these first 2 points align perfectly because that's what I used to calculate the initial velocity. Both graphs represent a linear relationship between position and time, which shows us our constant velocity. However, there are some discrepancies with the observed data. These discrepancies are due to an assumption that the velocity is constant. So looking back at the setup for our observed data, there must have been some net force acting on the soccer ball. So to more accurately model that motion, we need to take into account all forces acting on the ball, sum up their vectors, and reapply Newton's second law with a newly found non-zero net force. Next, I'd like to address the question of what if I flipped the axes? Or in other words, what if instead of saying that the ball was moving in the negative x direction, it was moving in the positive x direction? And what happens is that the position and velocity vectors keep the same magnitude. It models the same relationship. However, the directions are inverted. So what does this all mean? In this lab, we found a way to predict the motion of an object exposed to zero net force. The velocity is constant and is in the direction of the motion. The converse can be applied too. So if we're given a scenario where an object is moving with constant velocity, we know that by direct application of Newton's laws, that the forces acting on the object must sum to being net zero. Expanding further, we also know that an object experiencing changes in velocity, either with a magnitude or direction, must have a net force acting upon it. And with that, thanks for watching. Hope you have a great day.